All right. This is unmuted. Can you hear it? Yeah. And I muted it again. Okay. Okay. Yeah. Yeah. Oh, there we go. All right. Hello, hello, and welcome to Space Drafts number 104. My name is Nick Schragle. I am a fourth year graduate student at the University of Arizona and Steward Observatory. Welcome to Space Drafts. For those of you who are new here, Space Drafts is Tucson's version of Astronomy on Tap, a network of events sharing astronomy with the general public just like you in bars and pubs around the world. Our show is consisted of two 25-minute talks. We'll have a couple minutes for Q&A after each, and we'll have 20 minutes of intermission for you to go and refresh your drinks between the two. Each of those talks has a trivia question associated with it, which is your opportunity to win a little bit of our merch, which you can find over here. Speaking of merch, we have a table full of merch, which is available for you to buy. We only accept cash, unfortunately. But if you want to buy some merch, it's over here. We also do accept donations, which are very much so appreciated. All the money you put into Space Drafts goes into us making more merch for you to buy and keeping us running here. Before we get started, there is one last thing I have to mention. We are here at downtown location of Borderlands Brewing in Tucson, which means we are parked right next to an active train line. And so, whenever a train comes by to interrupt our speaker, ladies and gentlemen, what do? We raise our glasses and we say, "Choo-choo-choo." With that, I would like to introduce our first speaker today, here to tell us how to make gold out of neutrons. Please welcome Steward Observatory Theory Fellow, Dr. Aldana Grichener.
Excellent. Hi, everyone. Can you hear me okay? Great. Okay. So my name is Aldana Grichener. I'm a postdoc at the University of Arizona. And my research is basically based around the interface between astronomy and particle physics, which would mean that I studied the largest objects that we see in the sky, like stars and galaxies, and their connection with some of the smallest particles known to mankind that we can see only with a microscope. So today I will talk to you about the formation of elements and their astrophysical origin, starting with very light elements like hydrogen that is placed in the water that you drink or the oxygen that we breathe, and going on to heavier elements like gold and uranium. Okay, so the lightest elements that we know, like hydrogen, helium, and some other elements, are formed in the Big Bang. So the Big Bang was basically the beginning of the universe. There was nothing, and then there was this explosion, and everything occurred at once. And in the first 3 minutes after the Big Bang, we have the formation of hydrogen and helium that and in the gas that expands throughout the universe starts forming the stars that we see today. Okay, so in these stars, in the interiors of these stars, we what we have is also the formation of elements that of course also can be hydrogen and helium, but also somewhat heavier elements through the process of nuclear fusion. So what does it mean? It means that if we take now two particles, two elements which are the roadblocks that form everything around us, and get them close enough, then if we get them close enough, they could end up forming an heavier element, releasing energy in this process. And you can go on and take two hydrogens, forming helium, take two heliums for a carbon, etc., etc. And in different layers of the stars, we have different temperatures. So why is this important? It's important because it's hard for these elements to come closer, close enough to one another in order to form an heavier element, because they need to overcome some barrier of electrical charge. And notice that all the elements that are basically made out of particles that are called protons that are charged positively, and electrons that are charged with a negative charge. And when we get the two particles close, then they tend to repel from one another. But if we give them boost with really high temperatures, then at the end they will have enough energy in order to fuse and releasing energy in this process. So basically, this energy, what it does is that it is the thing that makes stars shine, but not only that it makes stars shine, it's also important for the life of the star because there's a constant battle between gravity and that wants to put the gas star inwards and this energy that basically takes things outwards. So the fact that we have this fusion of elements that release energy is what makes stars to be stable throughout most of their evolution. But the thing is that when we reach iron, then we actually can't overcome this barrier. We can't take like two irons and fuse them together into an heavier element. So that's all of this stops. And when it stops, then gravity starts winning. Gravity starts winning, everything starts collapsing. At some point, we have entire material that is becoming from all the protons become neutrons because neutrons are not charged, so they can sit closely together. But even for but even for the neutrons, it's still difficult to make this so close. So at some point, they keep compressing and compressing until it collapses, like stops all at once. When it stops all at once, there is like this enormous shockwave that goes throughout the galaxy with this explosion that basically outshines the entire galaxy for the time of the explosion, and we are left with this object that is called a neutron star. So a neutron star contains all the neutrons that were squeezed hardly together at the end of the life of a star. These things happens only for massive stars that are a couple of times heavier than our sun. Like our sun won't become a neutron star; it would become another thing at the end of evolution. But basically, these things are such weird objects because they're super dense. It's really like taking these neutrons are really like taking the entire material of our sun and compressing it into the volume of something like twice the area of Tucson. So this is a super weird element. It's like taking a teaspoon of this material of the neutron star would weigh about 10 billion tons. So they do really weird things throughout the galaxy. So keep these in mind because we will come back to them later in the talk. Okay. So we know how we form hydrogen, how we form the oxygen that we breathe, but we know that basically supernova are one of the most bizarre and extreme things that we have in the universe. But what we didn't talk about yet is how do we form elements that are heavier than iron. Like there are elements like gold, uranium, lead, things that we use in the industry or in our everyday life. We know they're in Earth because we detect them, we see them, but that we know that it can't be formed in this kind of supernova explosions because at the end, the part when we try to fuse two irons together to form something heavier would require to actually invest energy, and the stars don't like doing this because stars are at least they're lazy like all of us, right? At the end, what they try to do is to do the best that they can in gaining out of it, rather than trying to invest something out of it. So the way to produce these elements would be by capturing neutrons. So neutrons don't have electrical charge, so it's easier in this respect. So let's say we have an iron. So okay, we don't want to have like this bulk on iron, but they're really the molecules that stop the atomic particles of iron, and we have neutrons that are around. If they come closer together, then the iron ends up swallowing the neutrons. The neutrons that are inside the irons, they want to become protons, again, because protons are less massive, they're less energetic. So again, the star wants to do what it's best for its energy reservoir. And at the end, when they become protons, they actually change the properties of the material, because what defines what is an element different than the others, how many protons it contains. So at the end, if it swallows enough neutrons, this iron could become essentially gold. The gold can keep swallowing these neutrons that are around him and become something like uranium. And it goes on and on as long as we have neutrons around. That as long as we have neutrons around, we can basically form all these elements. And actually, having uranium is pretty important for the life on Earth as we know it, because we know that we have uranium at the core of the Earth, and the uranium is very unstable. It decays and it releases a lot of energy. So it basically keeps the core of the Earth boiling. So it leads to tectonic plates and to volcanic activity that would end up getting all carbon into the atmosphere. Plants around us, they take this carbon to do photosynthesis. They produce oxygen. So basically, even the oxygen that we breathe here today might come from the fact that this uranium was formed somewhere in the universe and it Earth. Okay, so we know how these heavy elements are formed, but what we don't know, or we didn't at least know up until a couple of years ago, is where this can happen. So throughout most of astrophysics history, we thought about these kind of things that can maybe happen in supernovae because okay, what we were thinking is what else is there? Like there's the supernovae, they're super energetic, they have all these conditions. So what else could lead to these conditions that are even more extreme than the conditions that bring? I should have everyone here as well. Okay, next time. Sorry? Try to talk over it quiet enough. Okay. Uh, It was actually a pretty good point. Like we had like this cliffhanger of where like these elements are formed, so pretty good timing. Okay. So you can hear me if I talk now, or should I wait a couple of more? Okay. So, basically, we were thinking about the supernova explosion and what else could it be there to form the elements. And we ended up in about a decade ago, or maybe a bit more, but this time it wasn't really mainstream, or to think about star collisions of two stars. So we are used to look at the sun, so we are not used to thinking about stars that are in multiple systems because the sun is alone. But the fact is that from observation, we know that most of the stars that are really, really heavy, that are a couple of times heavier than the sun, like to live in pairs. Okay, so these stars live in pair. At some point, one of them could end up in a supernova explosion, leaving a neutron star that we talked about earlier, while the other star is still burning these elements and didn't get to this point yet. So in the end, it could interact. The gravity of the neutron star would end up pulling the material from the star to itself and stripping the star. And then we will have another supernova with another neutron star. So what would happen is if these two neutron stars are really close, they can start like moving one around the other until they end up colliding, forming this really heavy neutron star that could end up forming a black hole. When the black hole is, first, for many astrophysical purposes, basically the neutron star with much heavier. But don't tell it to people that do general relativity because they will tell me to get off the stage right now. Okay. So basically, we have all this material that has lots of neutrons around, and these neutrons can be swallowed by iron or other things to form these heavy elements. And why does the neutron star get closer together? They get closer together because they emit something that is called gravitational waves. So gravitational waves are basically another form of, energy. It came from Einstein's theory of general relativity that said that instead of looking at gravity like this invisible force that is around every object that has mass and affects other objects around it, it looked at these massive objects as actually curving the space around them, or the space-time around them. So this curvature would end up telling the objects are to move, so they get closer, they curve the spacetime even more until they are close enough that it can collide. So in order to actually, this is really important because in order to even know that these theoretical things that we were thinking about, two stars, two neutron stars colliding, are real, we need to detect this signal of these gravitational waves and understand this. So there was breaking news in 2017. We can actually manage to detect these gravitational waves that come from these two neutron stars. But actually, there were even before that, like in 2015, we got the first ever detection of gravitational waves that come from from two objects in the sky, and this time it was two black holes. So how does it work? Drink, everyone. Okay. So how does it work? We have this really huge detector that is called LIGO. This detector, we do an experiment that it's so complicated that it took scientists about 50 years from the minute that started thinking about it until we actually built something that got the detections. Like in the early think like something like in the early 70s, we started actually thinking and designing this thing. And it was start operating around the early 2000, and actually, but the advanced thing that was actually meant for detecting gravitational waves was up in 2015. But it has here two really long arms that have mirrors. Between these mirrors, we have this light that is go from one mirror to another the entire time. And when a gravitational wave passes by, so it changes something in the light that actually makes a really small movement in these mirrors. So this actually the movement that we need to detect is so small that it would be equivalent to measuring the distance from Earth to the closest star to Earth, other than the Sun, which is called Proxima Centauri, which is about, I think, 25 trillion miles away, give or take, something like that, with a precision that is equal to the width of the human hair. So to understand like how crazy it needs to be and how sensitive this needs to be in order to be able to detect something like that. And the thing is that I remember the first detection in 2015 of two black holes that collided and formed gravitational waves. I remember because I was at the beginning of my undergrad, I was already doing some astrophysical projects, and I remember that like this was something that everyone were talking about. It was like such a big deal that it took my advisor about 8 hours from the moment of the announcement to prepare a public talk about how these things work and about the discovery. He announced that this public talk, I think, 4 hours before that. And even though he announced this spontaneous thing 4 hours before that, it still managed to fill out an entire auditorium with people that were like standing outside of the room trying to hear what he has to say about it. So this is like how much of a big deal it was like the confirmation of Einstein's theory of relativity. But I also remember from this public talk that I went that my advisor gave that people were super excited, but when they heard about all of these, there was kind of like, I would say, disappointed or disillusioned. And the reason for that was that like they say, oh, we need to like measure something to that amount of precision. I don't think it's true. Like everyone was saying like, no, it can't be like we are not quite there yet technologically. It can't be like we will never be able to actually know if this is something that is real. I will try to explain to them that there are not one but two LIGOs, one in Louisiana, one in Washington, and we saw like the same signal coming in both of them. But still people were pretty skeptical, saying it could be like, I don't know, a fly that like waved its wings at the detector and we wouldn't be able to tell the difference. Okay, so lucky for us, 2 years after that, in 2017, we actually detected gravitational wave from this collision of two neutron stars, the one that are important to form heavy elements. And this time we also detected the light that is coming from this event. So it was very groundbreaking because it was the first time we actually detected light that is coming, that it runs and that it has also this gravitational wave signature and also the light signatures. Actually, the University of Arizona was one of the first to detect the light that came from this event. The way that it works is that there was like an announcement that we have like this gravitational wave signature. Then all telescopes that are even remotely related to that went to looked at the sky and tried to see if we see the light that comes from this event. This time, because it was to a neutron star, the light didn't get sucked in, so it was possible to see it, but it's still very, very lucky. And other telescopes, like I think one of the first that detected the FEM there was called VLT, which is acronym for Very Large Telescope. So as you can see, like as astrophysicists, in theories, you can be like really creative in making a lot of models that are super, super creative. We're not even sure they're true to explain some of the observations, but when it comes to naming instruments, we come up with things like very large telescopes. So I don't know, the name stuck. Okay. So we were lucky that we were able to detect the light that comes from this event, but we were even luckier that we were able to detect also the heavy elements that come from this event, because we have these heavy elements that are formed that are really, really unstable. They are unstable, so they decay in a time scale that is of about, I don't know, a week, 10 days, something like that. And we can see the light that fits this decay. So you can see over here, like, how does it look like? And we have, like, here, this part, we have a laser string here. I don't think it works. Okay, we have, like, this part of the sky that was photographed a couple of years before. And there we have, like, this small segment that is, like, zoomed in over here when we saw the light that is coming from this event. And when we took pictures of this part of the sky, like, 2 weeks, 3 weeks after, then we basically again got back to this kind of picture. So this was something that was like it was such a big discovery that it was kind of like shown worldwide. Like maybe a couple of languages, just languages that I know people that they know. But basically, what we can see is that basically all over the world there were science segments of journals that went and said something about the discovery of these heavy elements in these two neutron stars. And curiously enough, we have also things that are not science related, like, I don't know, the Financial Times or the Wall Street Journal already detected them, though I think I suspect that I know why. If you don't see, like, most of them just say gold. So, but the thing is that this is actually a misconception because we didn't really detect gold, particularly in this kind of event. We think we have good reasons to think the gold is there because of other elements that we did detect, but for elements like gold that are really heavy, we don't have like the resolution and observations to actually see the gold there. Okay, so so we solved like a really big mystery of how elements are formed, which is all the heavy elements and how they're formed. But there's still one question that we are not really sure about, is that we know now for sure that these heavy elements are synthesized in these neutron star collisions, but we don't have enough of these collisions to explain all the heavy elements that we see. So you can see over here, Roy is like, I think like should be like the only completed graph that I show. You can see here observations of individual stars. Each one of these points is an individual star in our Milky Way galaxy. And here we have like the passage of time on the x-axis with the amount of a particular heavy element that is called europium. It's not as exciting as gold. It's usually we use it for medical imaging and the LED of our TV screens. But it's just an example of an element, though it's the same for many more of them. So we see here observations of stars that contain heavy elements in our Milky Way galaxy. And if we have like simulations of collisions of neutron stars, we could see that we don't have enough of these collisions of neutron stars to explain all the europium or heavy elements that we see. And actually, the solution for that is something that I've been working about for a couple of years now, which would be try and synthesize this heavy element instead of a collision of a neutron star with another neutron star, having a neutron star collide with another star, like a normal star that is 30 times or more heavier than our sun. So when these two stars collide, again, because the neutron star is so dense, it basically shreds the star apart, forming this disk around the star. And in this disk, we have many free neutrons that can also go for the formation of these heavy elements. And when I did the simulation of these fields, you can see that what we tried in the simulation was to reproduce the average of heavy elements per star. They're not the simulations don't try to reproduce like the scatter, but what would be the average, and we have a pretty good fit. Okay, so basically, this is my talk. Like my take-home messages are: we synthesize these lighter elements in the interior of stars in supernova explosions, and then distribute these elements around. For heavier elements, you probably need systems that have more than one star. Maybe we have two neutron stars, a neutron star and a star. And basically, the famous quote from Carl Sagan that we are all made of star stuff. Well, Arjuria is also made of star stuff. Maybe leave my trivia question here for you to win your awards. Okay, thank you. Oh, yeah. So the trivia question would be, where do we expect silver to be produced? Like the first option is the Big Bang. The second is in the interior of stars. The third option is in the outer layers of stars. And the fourth option is in the collisions of two neutron stars and the collisions of a star and a neutron star. So I don't know, what do I pick? Yes.
D.
Wait, which one?
D.
Yes, that's correct. Because basically silver, like gold, and like properties are similar to gold because it has like many protons, many neutrons. It's heavy, so it's producing these kind of collisions. Very good. Yes. So questions, anyone? Okay.
LIGO be able to see those star neutron star collisions?
Not in the next 40 years, I think. Maybe like we have this something that is called like these cosmic
Aldana, can you
or advanced like
can you repeat the question?
sorry, the question is, would LIGO would be able to see these neutron star and plus star collisions of systems the same way they saw the neutron star systems? So so the answer to that is that probably not. Like maybe in these advanced plans that we have for LIGO that are happen to launch like in a couple of decades, they will be like the resolution good enough in order to see them. But because this system would emit gravitational waves that are much weaker than the gravitational waves that come from the collision of two neutron stars, then we would need some sensitivity that is much higher, which we definitely won't be able to see with the LIGO that we are running today. Okay.
All right, so that takes us to intermission. We will be back here. Let me check the time real fast. It is currently it's 8 o'clock. Perfect. We will be back here at 8:20. Go refresh your drinks. Don't forget to tip your bartender. And if you want to buy some of our merch, we'll be over here at the merch table. See you in 20.
We're doing the video? I think so. Mm-hmm. Mm-hmm.
All right. Hello and welcome back. So, we have a couple of orders of business before we get to our second talk of the evening. First off, so in my introduction earlier, I said that Space Drafts is a part of the Astronomy on Tap network. And tonight is a very special night for Astronomy on Tap because we have a bunch of different shows happening tonight all around the world. So a quick question, shout out if you think you know the answer. If I can get a switch on the slides, please. How many Astronomy on Tap events do you think are happening today? Shout out if you think you know the answer. We got 11, 8, 6, and 3. I heard an 11, 8. Well, it turns out we have 11 happening today. And because Astronomy on Tap this is a new record for us, we've been asked by Astronomy on Tap headquarters to produce a little video for them. Each of the 11 events are giving them a little video. So what we're going to do, I'm going to ask if we could all coalesce in the center here for just a minute. I'm going to give a really quick introduction, just saying who we are, where we are, and then all of us are going to count as enthusiastically as we can from 1 to 11. Not sure why this is what they've asked us to do. So if I could have everyone kind of coalesce in the middle, so we can get this going, and then you can go back to your seats. What we're going to do is I'm going to give the introduction. We're going to count to 11, and at the very, very all do our choo-choo. Okay? Let's get the camera ready.
It's front and center. Right in the front. You want to come join us, front and center? Yeah, come join us.
She's gone.
It's a big production here today. Let's see if I can do this. All right, ready to go? Oh, we'll cut it down. Hello from Astronomy on Tap Tucson, aka Space Drafts. We are so excited to be one of the satellites having their events today, and we can count them for you.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Perfect. Thank you all so much. Okay. That will bring us to our second order of business before the second talk. We have an announcement from Jen Pearson.
Hi, everybody. So space drafts enthusiasts and astronomy lovers, I want to let you guys know that the Art of Planetary Science art show is this weekend. It's free. It's in the Kuiper Space Science Building on campus. It's from 5 to 9 p.m. on Friday, and then 1 to 5 p.m. Saturday and Sunday. Stop by, look at some cool astronomy-based art. The theme this year is Martian, and so looking at Mars and all that stuff. So we have some really fantastic art for you guys all to look at. Definitely stop by, swing by the campus, and take a look. Thank you all very much.
All right. Thank you, Debbie. Definitely go check that out. Yeah. All right. So, to bring us to the second talk of the evening, here to talk about the overabundance of black holes in the universe, please welcome Steward Observatory postdoc, Dr. Haowen Zhang.
All right, thanks for the introduction. And yeah, hi everyone. My name is Haowen Zhang, and I just graduated from Steward Observatory last year, and now I'm already a finishing postdoc here. Yeah. So in this last public talk in Tucson, I probably give, and I just want to talk about again the topics of my favorite research, the supermassive black holes, and some most recent findings by our amazing JWST telescope. So the title, as you can see, is we have found too many black holes near and far, meaning that not only do we find them in the nearby universe, but also in the early days since our Big Bang. Okay, so I think Aldana has already talked a bit about the stellar mass black holes that come from dying stars or stars that have merged together. But these supermassive black holes that I'm going to talk about are much heavier. They're at least 100,000 times more massive than the sun. And unfortunately, or maybe fortunately, we still don't know how these giant black holes have formed in the first place. We do know that, okay, choo choo, choo choo. Okay, great time. All right. Okay. So yeah, these black holes are black, of course, but um, we can actually see them because they induce very strong gravities on the matter around them. So, for example, in our very own Milky Way, we can see that there are so many stars and gas orbiting around the very center of our Milky Way galaxy. And by measuring the motion of these stars, we can calculate the mass of these central dark spots. And it turns out to be a 4 million solar mass black hole. And using the similar method, we can, and we have measured the black hole masses of many, many nearby galaxies because we can see, we can resolve the motion of these stars. For the black holes that are far, far away, unfortunately, we can no longer see the tiny motion of stars on the sky. So instead, to find these black holes, we have to rely on the huge amount of energy that they release when swallowing their surrounding matter and grow up. And when they're growing up by swallowing matter, they convert part of these matters into radiation, or in other words, light. And the result is that they will appear very, very bright on our images that we take with telescopes. And sometimes they even outshine the whole galaxy that they live in, that so that they will look like just stars on the images. So you might ask, okay, so we see these star-like images, but how do you know it's really a black hole instead of a star, right? So what we do is to take a specific kind of data called spectra for these objects. So what we do is that we use a type of instrument called spectrograph. Of course, it's much more fancier than just a prism, but basically what we do is to split the light using the spectrograph into different colors. And then we measure the intensity of all these lights of different colors and plot these curves. And we see that there are these telling features, these very broad and bright emission lines that only appear in the spectra of accreting black holes or growing black holes. We cannot see them in stars. So whenever we see these star-like objects and we suspect that they are black holes, we just take their spectra and we try to find these broad emission lines. And even better, we can even use these broad emission lines to weigh these supermassive black holes. And this is because these broad emission lines are radiated by the hot gas that are revolving around these growing supermassive black holes. And more massive black holes are able to trap all these, more massive black holes are able to trap more gas orbiting around them at a higher speed. That's why, and as a result, you would get broader and brighter emission lines. So by measuring the brightness and width of these emission lines, we can then back out the mass of the central black holes. And we can do this with lots of different telescopes. On the ground, we have been using, say, Magellan telescope on the southern hemisphere. And in the sky, we have not only the famous Hubble Space Telescope that was launched 35 years ago. And very recently, we also have this big shiny telescope that cost us $10 billion, JWST. And in fact, with this $10 billion, JWST is actually too good at finding black holes and galaxies that are far away because it has this amazing capability of detecting red lights well into the infrared wavebands. So it allows us to see the galaxies that are really, really far away in the early days of universe, whose lights have already been redshifted into infrared. So I guess the happy problem that astronomers are having is that JWST has found too many of these black holes, and many of them are just too heavy compared to our theoretical predictions, including my very own. So specifically, this orange line is the number of black holes as a function of their brightnesses from our theoretical expectation before we launched the JWST. And these red dots, well, they're actually hexagons, but I don't think you can see them. They are the actual detections by JWST, and they turned out to be 10 times more compared to what we expected. And okay, so this is too many black holes. And at the same time, we also measure the masses of these black holes. And if you compare these JWST data with the previous data that we found in the nearby universe, we'll see that these JWST black holes turn out to be 100 times more massive compared to what we would expect if we're just comparing them with their local or nearby counterparts. So another aspect of this problem is that lots of these black holes are just too heavy, and this is just the problem that we're having in the early universe, and that's not even the whole problem yet. So we actually have a similar crisis in the nearby universe that we found out by listening to the gravitational waves released by these black holes that are closer to us. So for those who are less familiar, gravitational waves are just basically wrinkles in space-time that are stirred up by these black hole pairs that are revolving around each other and all the way up until they're merging together. Okay, so when these wrinkles of space-time pass through our Milky Way galaxy, they will change the distance from a very specific type of light source called pulsars to our very own Earth. And the periodical, like this change in the distance would also change the time it takes for the periodical light signals from these pulsars to the Earth in a systematical way. So astronomers have been monitoring the change of this times of arrival of light signals and modeling how these changes respond to the gravitational waves and that are generated from the merging black holes. So given the current technology and how good we can build our instruments, we are still quite far away from, or at least a step away from, detecting or resolving the gravitational waves released by individual black hole pairs. And this is because gravitational waves are in general very, very weak. And for any individual pairs of black holes, the signals that they produce are just so tiny. However, we also have a effectively infinite universe, and there are just so many black hole pairs that are merging at any given time. So if we actually add up all these signals, all these tiny signals from each pair of black holes, then we can get a strong enough signal that we actually detected back in summer 2023. And this collective signal um, it turned out to be quite universal. You can hear it from every single direction of the sky. So that's why we call it gravitational wave. Sorry, that's why we call it gravitational wave background because it's basically coming from every direction. You can hear it from anywhere. Okay, so here comes the trivia question of my talk. So we have detected this gravitational wave background. Then which of the following black hole populations have contributed, or the biggest contributors to this detected signal? Is it A, 1 million solar mass black holes, or B, 10 million, C, 100 million, billion, or 10 billion solar mass black holes? Any guess? Just, yep,
100 million.
100 million. Okay. Any other answers?
10 million.
Okay. Any others? Okay, D, 1 billion. Okay. So the correct answer is D, 1 billion. And so the reason is that any black hole pairs lighter than this will generate two weak signals individually. Although there are so many of them in the universe, when adding so many tiny signals together, they still don't contribute enough to the collective signal. And for 10 billion solar masses, yes, they are individually very strong, but there are just too few of them because massive black holes are usually very rare in the universe. So yeah, it turns out that 1 billion solar mass is a sweet spot in terms of the strength of individual signals and also the number of sources contributing to what we hear. Okay, so what's the crisis? The crisis is that, again, we're hearing too loud a signal of gravitational wave background, meaning that there are actually many more merging black holes in the local universe than we have ever expected. So here in this plot, I'm showing in red the actual detection that we had back in summer 2023 from basically a international effort. We have teams from North America, from Europe, from Asia, and also Oceania, I think. And yeah, and these blue curves are my very own theoretical predictions, assuming different shapes of black hole pair orbits. And we can see that, well, no matter what the shapes of these orbits are, my predictions are pretty much always lower compared to what we actually detect. And in my defense, it's not just me. It's every other single theoretical predictions. They always lie below this actual detection. So apparently, we have been seeing way more supermassive black holes than we have ever expected, and many of them seem to be overmassive. And whether that's in the local universe, in today's universe, or in the early days that we have seen with JWST. So why is that? Um, I guess um, I guess most astronomers here would agree that we don't know yet. And personally, my favorite way of saying this is that, or of my favorite way of rephrasing this is that, please give us more research funding. Um, and yeah, before that happens, I do have some personal guesses about why this could happen. So the first possible explanation is that maybe we have been overestimating the black hole masses in the early universe. Remember that we have been measuring the black hole masses in the early universe using these broad emission lines. We have been using the scale for the early universe, but the thing is that we have to calibrate such scales using the black holes that we see in the local universe. We also know that the early universe is very different compared to what we see today or where we live today. Because to start with, the early universe it was much denser compared to today's universe. So with all these different physical conditions, maybe these calibrations just are off for the early universe. And maybe by miscalibrating our measurements or measuring tools, we're just overestimating the black hole masses. Okay, so let's say we are measuring these black hole masses accurately in the early universe. But the second question is, are these black holes representative of all the of all the underlying black hole populations in the early universe? Probably not. So astronomers keep saying that JWST is amazing. It beats every like expectation when it comes to detecting capability. But as good as it is, there is still a detection limit in terms of black hole mass, even for JWST. So this is because when we are measuring black hole masses with broad emission lines, when like for lower mass black holes, their emission lines are going to be too narrow and or too faint for JWST to measure well. So basically, in this regime, in this black hole mass range, we don't really know how many objects we have missed. So if there turn out to be tons of smaller black holes lurking here, then these massive outliers will be just a very biased population compared to the underlying part of the iceberg. So that would certainly change our knowledge of the early universe. Okay, so the third and final possible explanation is for the too loud gravitational wave background that we have heard, which is probably in the local universe, we have been underestimating the masses of galaxies. So just a recap, we have been hearing stronger gravitational waves from the local universe, which means that we need more massive black holes to be merging. So if astronomers have really been underestimating the number of massive galaxies in the local universe, then one thing we can do is to make a correction so that there are actually more massive galaxies. And we know that more big galaxies usually means more bigger black holes, because big galaxies usually host big black holes. So more big black holes will naturally lead to more black hole mergers that can contribute to this gravitational wave signal. And that will boost our theoretical expectation to match with what we actually observe. Okay, so all these three possible explanations are saying basically the same thing, which is astronomers haven't been measuring things very accurately. So I think to some extent that's probably true, or alternatively, our like theoretical astronomers haven't been making very good predictions. So at least one of them is true. This is probably a bit embarrassing, but I think this is also how scientific research, or more specifically astronomy research, works. We from time to time we come up with better instruments, better technology, or better theoretical models, and by examining our old results with these new tools and new models, we figure out where to improve on. So if you're interested in contributing to this effort, the first thing you can do is to donate more money, not only to the local Department of Astronomy, but also in general um, to other, basically all the different kinds of efforts to basically promote astronomy research and outreach. If you feel like you want to do the research yourself, feel free to apply for our grad school programs and apply for astronomy jobs. And yeah, so I think I'll just leave my kind of lengthy summary here. And if you have any questions or comments, I'm happy to take it. Thanks. Yeah.
Questions, if I may.
Yeah.
Do we understand what the purpose of black holes are? I mean, everything has a balance. Everything has a reason why it exists. Do we understand maybe what the purpose of black holes are?
Okay, so the question is, do we understand what the purposes of the black holes are? Why, like, what's the reason? Is that?
Everything exists. I mean, everything has a balance, right? There's a purpose for everything except for humans sometimes. But anyway.
Yeah, so I'm not sure if I know the answer to this question very well because I think for me personally, every physical being just form in the first place because the physical conditions are satisfied or are conducive to their formation. So there are hypotheses, different hypotheses for the formation of this kind of massive black holes. Like in the early universe, maybe the giant clumps of gas just they um, they tend to collapse before they form, like before they break down into small pieces to stars, but instead they just directly collapse into a supermassive um, star-like thing, and then they evolve super quickly into a black hole. There are also hypotheses saying that maybe the earliest generations of stars, when they die, they form tons of smaller black holes, and then somehow they just migrate towards each other and merge into these giant black holes. Those are, I guess, this is more like um, what are the physical conditions that led to the formation of these black holes? That's less like what is the purpose of the black hole formation.
And the reason I ask because if you say there's too many or there's a crisis, what is changing that causes them to appear more for a purpose, right? That's what I was kind of curious about.
Yeah, so I guess the it's not a crisis for like for its own sake. I would say it's more of a crisis for astronomers or for the existing theoretical models to explain the formation and evolution of these black holes. Yeah, but I would say every crisis leads to more opportunity for new discoveries. And I think you have a second question?
Well, that was kind of right. You said there's too many or a crisis.
Oh,
How
okay.
do we know, right?
Gotcha. Yeah.
Really nothing.
Okay, thanks. Yeah.
What kinds of observations would you want? What in your ideal, what kinds of observations would you want to like break these questions down?
So yeah, the question was in the ideal world, if we can get every kind of observation we can get, what would be the best observation to solve these tensions, crisis, whatever? So I think the first thing I would definitely die for would be a complete census of black holes in this low mass regime, so that we can know whether uh, there are really lots of things that we don't get to see with only JWST, as good as it is. And I guess the other thing that I would like to see is um, basically a definite answer of like whether we are really underestimating the number of massive galaxies, because so in the real world we can't the basically the number density of massive galaxies here is very uncertain because we only have so many of them in the local universe, and we're limited by a kind of statistic called Poisson statistics. There are only so many of them, so that's why they're uncertain. But if we have a infinite volume in the local universe, we can then measure these number densities infinitely well and see whether this could explain the discrepancy between the theoretical predictions and observations. Yeah. Yeah, please.
Are there any telescopes coming up recently that are get launched that will be able to solve and see or define?
Okay. So the question is, are there going to be, or have there been any telescopes that are launched recently, maybe more recent than JWST, to solve these mysteries? So that's, I would say it's not really so kind of unfortunately, no, the short answer. However, we don't really need to rely on a like even newer and flashier telescope to solve this, at least the gravitational wave mystery. So the reason is that the way or the instrument that we use to detect this gravitational wave background has been out there on Earth for at least 1 decade or 2 decades. And one very good thing about it is that it just keeps taking data, regardless of whether the data is used for gravitational wave detection. So once people, like, I think 10 or 15 years ago, people realized that this kind of pulsar data can be used to detect these gravitational waves, and they jumped on it. And then they realized that, okay, so now we have only detected this background, but if we can keep taking these data, which is very, very cheap, much cheaper than JWST, if we keep taking these data for like 10 or 15 more years, we can then get to the stage where we can actually resolve individual black hole mergers that's happening right next to us. So in like when we are reaching that stage, or like in 10 or 15 years, we can then know basically the properties of these gravitational wave sources and see whether they are really coming from these merging black holes, as we now have argued about. And also, like, exactly how many of these sources can we see in the local universe, and which will basically tell us whether we're predicting the merger of black holes correctly, whether we're predicting um, the um, the typical masses of these black holes in the local universe correctly. So it just takes more time, but it's gonna be a guaranteed, probably too strong with the word guarantee, but it's a very likely outcome that we'll know about more details of gravitational waves without having to send another $10 billion telescope into the sky. Yeah.
And then lead on to that. Are there any proposed ones that they're talking about now that maybe are going to launch in 5, 10 years?
Sorry, could you repeat the question?
Any more proposed, more accurate telescopes that are going to get launched in 5 to 10 years?
Yeah. So the question is, are there like more accurate or effectively more like flashier telescopes that are being proposed to be launched in 5 or 10 years? I think it's going to be hard, especially given the potential budget cut that's upcoming and already happening. Yeah. So if there are private funding sources that's big enough, we're certainly happy to take it and convert it into a big enough telescope to do. Yeah. Okay. Thanks.
All right, so that wraps it up for today's. Thank you again, Haowen. Today's spacecraft. We will be back. Let me check my notes here. We'll be back on March 18th, the same time, same place, right here at Borderlands. Don't forget to tip your bartenders. Don't forget about the Art of Planetary Science if you have time. Definitely go check that out. Thank you once again. We'll be here at the merch table for a couple minutes if you want to come up and chat, buy some merch. And yeah, that about wraps it up. See you on March 18th, same time, same place.